Okay, then I will start. So first of all, good morning to all of you. So this is the last day. Congratulations to everyone who made it till now. What we're going to do today are two things. I would like to spend an hour or an hour and a half talking about an algorithm, a Bayesian algorithm called the approximate message passing algorithm. It's a very important class of algorithms which are rooted in physics and communication, and which are often, let's say, the best algorithm you can imagine for a given problem. If it's, let's say, it applies to certain types of problems, but when applicable, it's usually the best algorithm we know. So it defines what we call the algorithmic limits, in the sense that we don't know any efficient algorithms that can beat this one, and so therefore it's really the one that defines the algorithmic phase transition. And usually the gap between the performance of the minimum mean square estimate, or the base optimal performance, and this AMP algorithm is what we call the statistical to computational gap, which was the hard phase, which I also call the hard phase at the beginning of the course. So that's why it's so important, not because it defines this algorithmic hardness. So it's a very important. Not only it's important for applications, but also it's very important from the theoretical perspective, because it's an algorithm you can rigorously analyze. And so by understanding its behavior, you can say many things about the problem. And then I will not derive completely the algorithm. I will just give you some ideas of what it is. And then I will spend the rest of the time to show to you a presentation that I had prepared for another event, which is about large number of applications of these techniques, and importantly the connections between statistical physics and information processing systems. Okay, let me just open one thing that I need. My phone. Excuse me, just give me 1 second. Okay. Yes. Okay. Right. So let's start. So let's say introduction to the approximate message passing algorithm, and also doing so I will introduce another connected algorithm which is called belief propagation. So from what I understood, many of you are coming from electrical engineering or communication background, if I'm not mistaken. If that's the case, you probably have heard about belief propagation. It's also called the max or or the sum product algorithm. It's one of the most important error correcting algorithm. It's a decoder that is used in modern communications a lot. And so, yeah. Okay, so let's start by recalling what's the goal that I want to why do we study this algorithm? Because if we go back to this picture here, there was 3 curves. There was the MMSE, which we have analyzed yesterday using the replica method. There was the spectral PCA, which we have analyzed the second day using random matrix theory. And there is this third curve, which is matching the minimum mean square estimator on the algorithmically easy regime and the impossible regime, not in the algorithmically hard phase. And this is this approximate message passing algorithm. So I want to tell you what it is. And this type of algorithmically hard phases, computer scientists call this statistical to computational gaps. So you see, because you have a gap between, in this region, you have a gap between what you can statistically achieve, so independently of the computational power you already spend, and if you fix yourself a computational constraint, you want efficiency, you can only reach that performance. So you have a gap between statistical and computational performance, okay? Computationally efficient performance. Perfect. Okay. So the first thing I'm going to do is present belief propagation. So we will see that this algorithm that, again, I think some of you have encountered is actually the approximate message passing algorithm in this quiz, in the sense that belief propagation is an algorithm which is used to solve inference problems on sparse graphs. Approximate message passing is just writing the belief propagation equations and applying them to a dense graph of like the Wigner spike model is, and doing some kind of central limit type of approximations to simplify the equations. So let me explain what I mean by this. So the first notion, so belief propagation is an algorithm that is used to perform inference on a factor graph. So what is a factor graph? Inference for factor graphs. So a factor graph is just a graphical way to represent certain types of probability distributions, which is very general, which are just probability distributions that can be written in a factorized manner. So that's why it's called factor graph. So let's say you have a probability distribution over X. It may depend on some parameters theta, let's say the data in an inference problem, the measured data. If this is a posterior, this would be conditioned on the data. So this is 1 over a normalization, and it's a product over A. So A is indexing the factors, not the replicas like yesterday. We're not talking about the replica method now. These are factors, which are just functions, psi A, of a subset of variables, xa, and that depend on one on parameters theta A. So xa is a subset of variables, xa1, xa cardinal of A. It has a certain cardinal, so maybe there is one variable in it, maybe there are 2, 3, 4, 10, it can be any number. It's just a subset of the original variables, okay? Subset of components of the original vector x, okay? Perfect. These psi a's are called compatibility functions or constraints. And they're non-negative. compatibility or constraints, okay, or just factors. Perfect. So
I had a question.
Yes.
So when you mean a factor graph, a graph as in like a graph in the mathematical sense, like nodes with lines?
Yeah, exactly, nodes and lines. Because once you have a probability distribution like this, I can represent it as a graph, as nodes and lines. Let me do it. So the factor graph associated with this probability distribution would be the following one. So I would place a node for every variable. So this would be x that enters my probability distribution. Okay. And each time in this distribution there is a factor, a function here that depends on a certain subset of these variables, of these nodes, then I draw a box and I connect these nodes to this box. So let's say this would be a psi, and let me index it by the nodes to which it's connected. This would be a psi 2, 3, 4, which is any non-negative function of x2, x3, and x4. And it may also depend on some additional parameters. That could be data, that could be anything. That could be also random variable itself. Okay, so this is a factor. I could have a factor there. This would be a psi 1, 2. I could have a single factor there. So this means it's a function of psi 3 only. And so on.
So okay. Are the factors, are they like hyper edges?
Yes, they're hyper edges, exactly.
Yes. Okay. Yeah, also excuse me for not showing the camera, it's early.
Yeah, and thank you for being there and proactive, actually. Thanks, Joe.
But next session.
Yes. So yes, these are hyper edges. So these are hyper edges in a hypergraph. Yeah. Perfect. Okay, so this is so you can think equivalently of this graphical representation or as this probability distribution. They encode the same information. So if you know this graph, if I give you this graph, you can write the associated distribution and vice versa. Okay. So once you have a graph like this, to write down the probability distribution, it's very simple. You take all the factors, all the boxes, and you make a product over them, and then you normalize. So this 1 over this v is just the sum over all values of x of this product of factors. Okay? So you have equivalence between the two. Perfect. So now that we have a notion of factor graph, what's the task? It's to perform marginalization. So we want to do inference, and to do inference, we do that through marginalization. So it means that given the joint law of all the x's, okay, I will emphasize that it's a big vector here, I will drop the dependence on theta, okay, but this law again can depend on some additional parameters. The goal is to obtain the marginals. Let's say there are n variables, okay. Because once you have marginals, you can make decisions, okay? So, for example, the Bayesian optimal estimator, you remember, the x base which is the posterior mean, given the data. This is really the vector of marginal means. X1 given Y, Xn given Y. And these are the expectations. This is the integral with respect to P x1 of x1 dx1 and so on. So you see, if I have access to the marginals, I can compute Bayesian estimators, and I can also compute the MAP estimator, the maximum a posteriori. Okay, I can maximize the marginal for every component, and so on and so forth. So I can make decisions which can be optimal. Okay, so this is really the goal: is to go from the joint distribution to the marginals in order to perform inference. Okay, so belief propagation is an efficient way to compute the marginals on rather generic factor graphs.
So when you say make a decision, what do you mean? Choose a certain variable?
Yeah, choose a value for the variables. So for example, if we're talking about an inference problem, the factor graph would be a posterior distribution, and these thetas would represent the observed data. Okay. In this case, you would like to extract an estimator for these unknown parameters. Okay, and so you would like to compute, let's say, the posterior mean, the minimum mean square estimator, which is the vector of marginal means, right?
Mm-hmm.
It means you need the marginals. But you can also do that. You can use that in a combinatorial optimization problem. Let's say you want to minimize a complicated function. This function is parameterized by a big vector, and you have constraints that between these variables represented by these factors. For example, the coloring problem, which is a hard combinatorial optimization problem, tells you that if two nodes are connected, then they cannot take the same color. Okay, so let's say you have 4 possible colors, so 4 possible values for each variable, and you are enforcing that if two variables are connected by an edge like this, they cannot take the same color.
Yes.
And you're looking for configurations of the axis that verify this. It's called a coloring. Then what you need to do is to obtain the marginals, and then what you're going to do is to attribute every node. You're going to select the color of every node according to the marginal. You're going to take the maximum of the marginal for every node. It's the maximum a posteriori estimator for every node. Okay, it's again an inference problem, but in the context of combinatorial optimization. Is it clear?
Yes.
In this case, the probability. So if you have a combinatorial optimization problem, these factors would be 0 if the two nodes are of the same color, in which case the probability would be 0. As soon as you have one error, one constraint which is not verified, this measure is 0, and otherwise it is 1. For any other choice, it's 1. So you are looking for these colorings such that and this probability distribution would kind of weight uniformly all these colorings, and any other choices would have 0 measure, and you're trying to sample this measure. It's the same. Okay.
Yeah, it's the coloring problem is very similar to a Potts model.
Yeah, it's a Potts model. It's the same. Yeah.
Yeah.
I'm saying coloring because maybe for non-physicists it's but of course you can also think of this as error correcting codes. These constraints would be let's say could be parity checks between bits. These would be bits, binary variables, And one factor like this would be a parity check. It would enforce that the sum of these two bits is an even number, for example. And so you are constructing a code like this. And then you receive a noisy version of those parity bits, and you try to reconstruct them. And so what you're going to do is to run belief propagation. You're going to try to sample to find configurations that are in agreement with all these these parity checks, and this is decoding. Okay, you are decoding. Okay. So actually, this belief propagation I'm going to write was discovered. It is really at the core of two communities. It was discovered by Gallagher in the 60s in the context of error correcting codes. He was an engineer. And it was also discovered independently, let's say in the 70s, in the context of spin glasses. So it's what we call in physics the cavity equations. It's the same. Okay. And it's one of the main tools to study spin glasses and spin models in general. Okay, so let me try to write these equations. Okay, but really the goal is to solve this problem. It's the marginalization problem. You have a joint distribution, and you want to look at to compute marginals. So of course, computing the marginal directly in general is a hard problem, right? And that's why you need an efficient way to do it. Because if I want to compute, let's say P of x1, I need to integrate over all the variables. But the first of the joint law. And this has in general a volume Rn minus 1. So it's a very high dimensional integral, right? So I cannot compute it. So you need an efficient way to do so. And that's where belief propagation enters into the... Perfect. So let me directly write the equations and then discuss them. So belief propagation. So for I equal 1 to n, the number of variables, and a equal 1 to m, the number of factors, I'm going to define two types of so-called messages, which are themselves probability distributions. They are the factor to nodes messages at time t that depends on xi, which is equal to 1 over a normalization of the integral of the factor psi a that depends on this set of nodes to which it is connected, product of all the nodes j connected to the factor a. So this notation means the neighborhood of a, except the node I, okay? And then I look at all these nodes. They're sending themselves messages towards A without a hat. It's the other type of message. These are with a hat. So these are factor to node messages. These are nodes to factor messages of xj at time t, and I integrate the xj. And then the node two-factor message, which also depends on I and in which is a well-normalized probability distribution, is just the product over all the factors B that are connected to I in the neighborhood of I, but factor A. And I look at all the information sent by these factors to xi. Okay? So locally, if you want, you can think of so the first. Let me move this and make drawings. The first type of messages, so it's a factor to node, which is connected to other factors, and this factor is connected to other nodes, okay, and so on. So this is the node I, which is receiving the message. This is the factor A, which is a box. And we're looking at the message sent from A to I. What is it? It is just the product of the messages that are going towards this factor from the other nodes to which it's connected. These are these guys here. But I'm not considering the one coming from I, because I'm sending to I. So I'm making the product. You should think of this as kind of marginals. Marginals, the best, so I will give you the meaning more precisely, but these are probability distributions. And then I'm like integrating out these marginals against this factor in order to obtain something that depends only on xi. Okay, so I take this function, I integrate out these variables according to these probability distributions, and I obtain something that depends on xi only. So what's the meaning of this quantity? It's called also a cavity distribution, because what I'm doing is like I'm doing a cavity in the sense that I'm cutting this edge there, as if this factor was only connected to these nodes here, but not that one. And I'm looking at what is the information that this factor only sends to this node. So it's like if I was, sorry, it's like if I was cutting there. Said a mistake. As if I was cutting this edge there. So this node, from when computing this thing here, it's as if it was only connected to this factor. So I'm disconnecting to all the rest of the graph there. And I'm looking at what's the marginal distribution of this node in this modified graph where all this part has been removed. And I'm only considering this part of the graph. Okay? And in this case, its marginal distribution is indeed given exactly by this. This is correct. You see, because if there is no other part there, the only connection from this node to the rest of the graph is through this factor. And in this case, this equation is exact. Okay? So I'm digging a cavity or cutting an edge, removing all this, and computing the marginal distribution of this node in this remaining graph, which we call also the cavity graph. Now, what is this message here? So I have a node, still node I, that is sending information to factor A, which is itself connected to other nodes. And this node is connected to other factors, which are connected to other nodes. So what I'm doing, yes.
Oh, sorry. Yeah, I was thinking, so the message passing, the M, it seems to resemble some sort of incidence matrix, like from edges to nodes.
Yeah, I mean, which A is sending to which I and vice versa is related to the adjacency matrix of the graph. Yeah, the adjacency
the incidence. Yeah, so the incidence is mapping the nodes to the edges, and so if we have A as edges,
yeah,
okay, of course, when you take the matrix product, you get the adjacency matrix, but.
Okay, yeah, you're probably right.
Oh, okay. I'm not sure. Yeah, I'm not sure. So M in practice is an array of numbers. Like
no,
if you
M.
Actually...
No. M really, this is a probability distribution. This is a normalized probability. It's a number between 0 and 1 for every xi. So it tells you what's the probability to take the value xi for the variable x.
Okay. Normalized probability. Okay.
Yeah. It's a well-defined probability distribution. So this is a normalization.
I see. Yes.
Okay, so this z here is the integration of this with respect to xi as well. So that the integral of this object with respect to xi is 1.
Exactly.
Okay.
So if M is a matrix, let's say with index A and I, if you sum over I, it should be 1.
Yeah. Yes, you're right. You're
Okay.
correct. No. You don't sum over I. You sum over x. So I is fixed, and you sum over the values of xi. So let's say if we're working with binary variables, let's say bits, the sum of this with xi equals 0 or 1 is 1. Xi is the argument for a given I. Okay, you're not summing over I.
I see.
Okay.
I see. Okay.
Thanks for the clarifications. So now the other messages, what they are. So the message from I to A is the product of the messages coming from the other factors. You just make a product to send this one without considering the one coming in that direction. So it's as if you're creating a chaotic graph by cutting here. Now you're saying, what's the probability distribution? This object is the probability distribution of I in a graph where this edge would not be present. So it would be connected to all the factors that it is connected to in the original graph, but this one.
So here messages from I to A should be the sum of the messages, or either sum or product.
No, it's a product.
So once it is a product and we are dealing with the binary thing, then the result will be 0.
So the result will be 0 if what?
Sending the binary messages either in the form of 1 or 0.
No. These messages are not binary. So let's say when I said binary, I meant the argument can be binary. But still, this would be a probability distribution for a binary variable. So it's still a number between 0 and 1. Okay? But these numbers some of them could be 0. Then the output is 0. It means that, so for example, if this constraint is telling you that some value can be
the product, the output will be 0.
Yeah, it can be, the product can be 0. If one of these messages is 0 or there, the resulting message there is 0 as well.
If the product is 0, then loss of information will be there in the channel.
No, because if you think in terms of coding, the observations from the channels have been obtained, and now you are just doing you are the inference step, you are the decoding step. So it's not so the communication has been done already, and now given the data, you're trying to decode the bits. Okay, and so depending on what's the communication channel, the model for the noise, etc., some sequence of bits have a non-zero probability to have been transmitted given the noisy observations that you got from the channel. Some have 0 probability, and so you are trying to find those configurations that are allowed, those sequences that are allowed, and to find, in general, in coding, you're trying to find the most probable one. You're trying to do maximum likelihood, and you can do that with this algorithm.
Okay, sir.
Okay, perfect. So these are the two types of messages, and why is this natural algorithm? So these are, again, the factor to node and node to factor message. Why is this an algorithm that you should... yes, and one thing I want to add is that once you have all these messages, let's say at convergence, the BP approximation to the marginals of the marginals is given by mi at convergence, so when t is infinite, which is an approximation of the true marginals, which can be exact or not, is the product of all factors. Now I'm not removing any. I'm really making the product over all of them of MA to I xi, which I then normalize. Integral of this numerator. Okay. So I'm considering, if you want, all the messages now that go toward the node from all the factors, and this is my approximation of the marginals, which can be potentially exact, if the, and then it can also not be exact. It depends. Okay. So in particular, I want to give you one case where this calculation is exact, in the sense that this you are guaranteed that this is really the integral over all x's except xi, I will denote it like this, of the joint law, which is indeed P of xi, the marginal. There is one case where you can prove that this is really an equality. And this case is when the factor graph is a tree. Okay, so theorem. BP is computing the exact marginals if the factor graph is a tree. So there are no loops. Okay, so for example, this is a tree. There are no loops. Okay, so if you start from any node or graph and you want to go to another one, there is only one path. Okay, so you can show it by induction. I won't do it, but what I recommend that you try is just to prove it by just running a small example. So let me give you an example, and then I will give you the solution and just ask you to verify it. So let's say that you have the following factor graph. Psi1, x1, psi1, 2, 3, x2, x3, psi 3, 4, x4, psi 4, psi 4, 5, x5, psi 5. So this is a tree. Okay, it almost looks like a chain, but you have this slight differences. So this is a nice tree. So, and let's assume that our vector x, which is x1 until x5, takes values in -1, 1 to the 5. Okay. So let's assume you are interested in computing the marginal of x1, or another problem you can solve with belief propagation, which is actually the exact same problem as the marginalization, is to compute the partition function, the normalization of the factor graph itself. So let's say you want to compute z. Yes. So how do you compute partition functions from these equations? You just this is the same problem as the marginalization. You just call these messages z's, and you do not normalize. And if you are doing so, you are computing at the end. You can reconstruct the full partition function by just making the product of all these quantities at convergence for all x's. So, of course, computing the normalization of probability distributions or marginalizing, which is integrating all variables but one, instead computing the normalization is computing the integration with respect to all variables, are of course the same problem. Okay, so let's say that you are interested in computing the partition function. So z is sum over x. So I will do the example at to the 5. Okay, so we have 2 to the 5 possibilities to sum over. And what's the normalization of the distribution? It's the distribution is just the product of the factors. I will not denote all the arguments because it's clear from the notation. Psi 1, 2, 3, psi 3, 4, psi 4, psi 4, 5, psi 5. Okay? And look, I can do something smarter than trying to compute this directly. This sum requires a number of operations, which is 2 to the 5, which grows exponentially with the number of variables. The number of variables is at the exponent there. What I can simply do is exploit this tree structure, this way the variables depend on each other, to simplify this computation. How? By just realizing that I can rewrite this sum like this. Sum over x1, which now just takes 2 values, minus 1, 1. So there are only 2 numbers. Of psi 1, I isolate the part that depends only on x1. Then I push on the right everything that depends on x2 and the rest. So x2 and x3. Okay, psi 1, 2, 3. Then x4, psi 3, 4, psi 4. And then I push there psi 4, 5, psi 5. Right? This is the same object, of course. I've just pushed the sums in a smarter way. Okay? I've distributed the sums. Okay? And now let's count how many operations does this computation requires, which is the same computation. So here we have 2 operations to do. We have 2 there. Here we have 2 to the power 2, which is 4. And here we have 2 as well. So in total, we have 2 plus 2, 4, plus 4, 8, 10. 10 operations. So you see, we went from 2 to the 5, which is 32, to 10. We have reduced the complexity. So it doesn't look like a big gain going from 32 to 10. But I claim that here, the computational complexity of this algorithm, if the graph would be much bigger, would scale linearly with the number of variables. Linearly with the number of variables times, so n times the maximum degree. Because you see here, if there is a sum that I cannot divide in 2, this is still exponential. The number of operations is still exponential in the degree, in the number of variables in this sum. So let's say the maximum degree of these factors is 2, 3, 4, something small that does not depend on n. The computational complexity of exploiting this tree structure would now require a number of operations, which is the number of variables times the maximum degree, essentially. So this is linear in n. Instead, here, this is exponential in n. So you see, by just distributing the sum, you go from exponential to linear, if there is a structure that allows you this distribution. And such a distribution is exact. You can do that if the graph is a tree. And belief propagation is exactly doing this on graphs that are more complicated than this, than something that just looks like a chain. And indeed, what I ask you to do is to realize that these computations, this first sum and the second one, etc., can be computed, are exactly computed from these equations. If you write down the belief propagation equations for this graph that I wrote there, you will realize if you unfold the equations, you really write all the equations, you will realize that what you're computing is this. You are distributing the sum. Okay? So that's why it's exact on a tree, and that's why it's also efficient. The computational complexity is linear.
Can we discuss this example with another type of graph, something in a mesh topology or any other topology?
What topology, sorry?
Can you discuss same problem with any other topology? Like you have discussed this particular graph with the tree topology, where you have taken all the nodes in a linear fashion.
Yeah, but the same example would work if you want. Here, if I start to branch another tree of any sort.
Yes.
It works exactly the same way. I could add also here factors which themselves branch. I mean, I can do something much more complicated. As long as it is a tree, it will work the same way.
The same BP equation will work on that particular graph also.
Yeah, of course. If the graph is a tree, belief propagation is exact, and it's exploiting the same kind of mechanism. It distributes the sum in the smartest possible way. It's exactly the same. I just don't want to write it because it becomes, of course, complicated. So that's why I took a simple example, but it's exactly the same. It works on any tree. It's exact on any tree.
Okay, sir.
Because what it does, it's really distributing this sum is distributing it. Okay. So you should try. You should convince yourself of this fact. Okay. So, okay, I'm a bit long, so let me try to just say a few words about the approximate message passing. So we have this exact algorithm on a tree, but the subject of this course was the Spike-Wigner model. The Spike-Wigner model. And what's the distribution of the Spike-Wigner model, the posterior distribution? It was 1 over z, the posterior, times the prior, times the likelihood. Okay, so I can think of this as a factor graph, where this would be my factors psi, excuse me, there's a bug, psi i's of xi, so the prior plays the role of single factors, and this would be pairwise factors, psi ij. That depends on xi and xj. So the Spike-Wigner model, like any distribution which has some factorized structure, is a factor graph. But let's draw this factor graph. So let's say we have 4 variables. x1 is x4. I have one factor per variable, which is the prior, psi1, psi2, psi4. And then for every pair, I have a factor psi ij. So I have one factor there. This will be the psi24, one there, one there, one there, one there, one there. So this factor graph is anything but a tree. It's precisely the complete opposite of a tree. It's a fully connected graph. It's a fully connected graph. So why would I be spending an hour talking about an algorithm which is guaranteed to work on trees and try to connect that to an inference problem defined by a factor graph, which is the complete opposite of a tree? The reason is that belief propagation does work on this type of graphs as well. Okay, so the fundamental reason why belief propagation. So first of all, belief propagation is guaranteed to work on tree, but you can also run it on graphs which are not trees. So like usually BP was used to solve inference problems on locally tree-like graphs. So graphs which are sparse. It means that the average degree of nodes and factors is not dependent on the size. So if you increase the graph, you multiply the size of the graph by 2, the average number of neighbors of every node and factors remain the same. This is called a sparse graph. And in this case, there is a property which is the fact that every local neighborhood of any node or factor is a tree. So if you take a big enough graph with an average degree which remains bounded, which does not depend on the size of the graph, then in the limit where the graph becomes very large, every local neighborhood, so if you zoom anywhere in the graph and you don't look at the rest, it will look like a tree, okay? And therefore, you may hope that despite that there are very long loops in the graph, because of this locally tree-like property, the algorithm may work. And indeed, if these loops are not too many, belief propagation works and perform exact inference, okay? But at some point, if the average the average degree becomes too large or there are too many loops, the algorithm may start to fail. And this is why you start to have a computational gap, a hard phase. At some point, there are too many loops and the tree approximation becomes too wrong. The algorithm does not perform well, and you have this mismatch with the optimal performance that you would get if you could solve the marginalization problem exactly. Okay, but you can hope that BP works also if there are loops. The issue is that here there are only loops. Okay, it's not locally tree-like. It's not sparse. It's the complete opposite. It's totally connected, this graph. But nevertheless, BP works. And the fundamental reason is that like in tree-like graphs, these fully connected graphs are such that if you look at the dependency, let's say the amount of dependency, so this is informal what I'm saying, between any two variables, even if they are directly connected by an edge. So in such a graph, there is no neighbors. Everyone is neighbor of everyone. There is no distance. Okay, it's not that some nodes are further from some others. They are all directly connected. So every neighbor, every pair of nodes, the point is that they are weakly dependent on each other. Like in tree-like graphs, it simply comes from the fact that most nodes are very far away from all the others. So the information that propagates from one to the other is passing through many other nodes, and somehow this dilutes the amount of dependency between variables that are far away. Here, variables are all neighbors, but the point is that look at a given variable, let's say this one. It is true that it is connected to all the others, but the point is that each of these interaction, for the model to be well defined, or at least for the model to be solvable by this kind of algorithms and techniques, should be weak. You see, and here it manifests itself by the following fact in the Wigner-Spike model. One of these interactions, psi ij, which is represented by one of these factors, is a function. It's a Gaussian distribution of xij. I mean, it's a Gaussian where xij appear like this in the mean. But you see that we have this 1 over square root n there. Okay, so this is a very weakly dependent function of xij. Okay, this mean is tamed down by this scaling, this 1 over square root n. So you see that if you do a Taylor expansion of this, for example, at first order, it does not depend on xij. You need to go in higher order to see the dependency. So you have a really weak dependency enforced by these factors between any two variables. So it's a bit like a tree-like graph. It's as if these nodes were very far apart. Okay, and therefore belief propagation does work, surprisingly. At least in some regions, it does work if you are away from this algorithmically hard region, which is the region where the effect of these loops become too important. Okay, at some point this breaks down, but somehow there is a region where, due to the fact that every interaction here is weak, which is as if the nodes were very far apart, so the graph behaves a bit like a tree, then BP works. Okay, so the IMP, okay, so it's 9, so maybe we can stop there. I will use half an hour of the next lecture to tell you how to go from this belief propagation equation. I mean, I will just give main conceptual steps to go from this belief propagation to the IMP algorithm, and then we'll stop there, and then I will present the applications part of not just IMP, of statistical connections between statistical physics and inference and learning. Okay.
Okay, sir. Thank you so much. And we'll start the next session after 1 hour, that is at 1:30, sir.
Yes.
What time will start?
Yeah. We do the normal schedule, so it's 1:30 for you. It's in 1 hour.
Okay, sir. We'll start the next session at 1:30. So thank you for the informative session. This session was really very good. I understand a lot of things. How a linear fashion, how exponential can be converted to the linear, how BP equation can be implemented in trees and other type of graphs. So it was very informative session, and all the participants are requested to join the next session after 1 hour.
Okay, thanks.
Thank you, sir.
Goodbye.
Okay, thank you, sir. Goodbye.
Thank you.